Scientific notation. International travel to the United States is big business. So big, we can use numbers written in scientific notation to describe it. The table shows the amount of money spent by international visitors in a recent year. Order the countries in the table according to the amount of money visitors spent, from greatest to least. First, we'll group countries together based on their exponent. Canada and the United Kingdom both have exponents of 10 to the 7th power. That's 10 million. Mexico and India have exponents of 10 to the 6th power. That's 1 million. Since the exponent for Canada and the United Kingdom is greater, tourists from Canada and the United Kingdom both spent more money than tourists from Mexico and India. Next, look at the groups individually. Since 1.06 is greater than 1.03, tourists from the United Kingdom spent more than tourists from Canada. Since 7.15 is greater than 1.83, tourists from Mexico spent more than tourists from India. So, in order from greatest to least, the countries are the United Kingdom, Canada, Mexico, then India. Let's check our progress by trying another exercise. The table lists 7 of the top U.S. cities visited by overseas travelers in a recent year. Order the cities according to the number of arrivals, from least to greatest. First, group the cities by their exponents. Boston and the Metro D.C. area have exponents of 10 to the 5th power. Las Vegas, Los Angeles, New York, Orlando, and San Francisco have exponents of 10 to the 6th power. Since 5 is less than 6, Boston and the Metro D.C. area have the least amount of arrivals. 7.21 is less than 9.01, so Boston has the least number of arrivals. Look at the next group of cities. From least to greatest, there is Las Vegas, San Francisco, Orlando, Los Angeles, and New York. So the order of these cities from least number of arrivals to greatest number of arrivals is Boston, the Metro D.C. area, Las Vegas, San Francisco, Orlando, Los Angeles, then New York.
This is Mr. Hardesty. Let's express a number in standard form. Write 6 27/100 times 10 to the 3rd power in standard form. When we multiply by a power of 10, as we're doing in this expression, we know that each power of 10 represents a move of the decimal point. That is, 10 to the 1st power would move 1 decimal point. 10 to the 2nd power, or multiplying by 100, moves another decimal point. And finally, 10 to the 3rd, or 1,000, moves 1 more decimal point. So we would have 6, 2, 7, and a 0 in here to account for that last decimal point. And in standard form, we would have 6,270 to represent this same value, 6 27/100 times 10 to the 3rd power.
Hi, this is Mr. Rutherford. In this problem, we will learn to express numbers in standard form. Write 5.23 times 10 to the negative 4th power in standard form. So what we need to do here is write this without the times 10 to the negative 4th power and express this as a decimal that's not in scientific notation. We have 5.23 times 10 to the negative 4th power. The negative 4 in scientific notation indicates we need to move our decimal spot in the 5.23 to the left 4 spaces. So we'll write that down to remind ourselves. I'm going to recopy our 5.23, and we'll move this decimal 4 spots to the left. Now we need to fill in zeros before the 5. So this equals 0.000523, which is the standard form of our original problem.
Hello, this is Mrs. Workman. Write 4,560,000 in scientific notation. Scientific notation is a method for writing very large or very small numbers. This is a rather large number, so we want to rewrite it in scientific notation. Scientific notation is a product of two numbers. The first number is a number that's 1 or greater than 1, but less than 10. The second part is a power of 10. Let me show you how this works. I'll write our large number, 4,560,000. To find the number that goes here, we put a decimal point after the first non-zero digit. So that would be right after the 4. And we're going to write now 4.56. And I don't need to write all of these zeros. The next thing we do is we need to find a power of 10. To do that, we're going to see how many places we'd have to move this decimal point to get it back to where it is in the original number. And that would be 1, 2, 3, 4, 5, 6 positions. In other words, I'd have to multiply by 10 to the 6th power. If I would multiply 4 and 56/100ths times 10 to the 6th power, I would get 4,560,000. This is the scientific notation way of writing that large number.
This is Mrs. Dawson, and the following is a real-world example involving space. The table below lists the distance of each planet from the Sun. Order the planets from greatest to least according to their distance from the Sun. Notice that they are all in scientific notation, with 1 digit in front of the decimal. Because they are all in scientific notation, we can focus on the exponents. The numbers that have the 10 to the 9th power are going to be the highest numbers. 10 to the 8th power will come next, and then 10 to the 7th power will be the lowest number. Let's begin with the 4 highest. 4.51 times 10 to the 9th, 5.91 times 10 to the 9th, 1.43 times 10 to the 9th, and 2.87 times 10 to the 9th. Are the 4 highest numbers, and now written in order. Next, we'll go to the planets whose distance from the Sun is with a times 10 to the 8th. 1.50 times 10 to the 8th, 7.78 times 10 to the 8th, 2.28 times 10 to the 8th. And Venus down here at the bottom, 1.08 times 10 to the 8th. So far, we know that these are listed in order from top to bottom, and they are all greater than the ones in red listed in order from top to bottom. The only remaining planet is Mercury, with a distance of 5.79 times 10 to the 7th. So our planets listed in order are Pluto, number 1, Neptune, number 2, Uranus, number 3, Saturn, number 4. Moving to the next 4 in order, Jupiter, number 5, Mars, number 6, Earth, number 7, Venus, number 8, and finally Mercury, number 9.
Welcome to McGraw-Hill Personal Tutors. Fleas can jump 200 times the length of their bodies, which can be up to 33 centimeters. Is it more appropriate to report this number as 33 centimeters or 3.3 times 10 to the negative first meters? Our choices are 33 centimeters, or 3.3 times 10 to the negative first meters. The number 3.3 times 10 to the negative first meters is a very small number, so choosing the larger unit is more meaningful, which means in this particular problem, 33 centimeters is more appropriate. Thank you for using McGraw-Hill Personal Tutors.